course, as mentioned, after you have to plot the result from your trial for that liquid limit. And as we have discussed, as we try to trace or draw a connection between these dots, this is what we call as flow curve. So this is a flow curve for liquid limit determination of a clay silt. So for the flow curve, you have here the the relationship between the moisture content and the N, which is the number of blows needed to close the gap. So it is assumed to be linear. So for the flow curve, we have this equation. This is the equation for the flow curve. So this expression, I sub F, is what we call the flow index. And for the flow index, you're going to have this formula, wherein flow index is equal to the moisture content of soil in percent corresponding to N1 blows, and this one is the moisture content corresponding to N2 blows all over your N sub 2, log of N sub 2 all over N sub 1, and of course represents the number of blows. So you just have to substitute the given values, and you can have this I sub F, which is you can substitute so that you can have the flow curve. So we have here before this is also another method to estimate the liquid limit, which is what we call the 1-point method. So based on a single trial, and it's generally valid only when N is greater than N, or the number of blows is greater than or equal to 20 but less than or equal to 30. So you can have this expression using the 1-point method that the liquid limit is equal to moisture content multiplied to N, which is the number of blows, over 25. And here is the number of blows required to close the groove. And this is raised to tangent beta, and your beta is equivalent to 0.121. Your Wn refers to the corresponding moisture content. Moisture content as it closes the groove or in our trial. So we have here corresponding values for our N all over 25 raised to 0.0121. So you just have to obtain the corresponding number of blows on this table. Then we have what we call fold code method. Fold code method is also used to identify the liquid limit. So for this fold code method, it defines the liquid limit as the moisture content at which a standard cone, apex angle of 30 degrees, weight of 0.78 Newton, penetrates 20 mm in 5 seconds when dropped from point contact with the soil surface. So for this one, you have your figure illustrates the fold code method. So for the fold code method, you're going to have here our soil sample placed on a container, and you have a cone that is having a weight of 0.78 Newton. So how are you going to, of course, this is the standard measurement, 55 by 40 mm. So once you have the setup now, you're going to drop the cone into the soil sample, into the container where there is the presence of your soil sample. Once you drop that one, you're going to measure the depth of penetration. So this is the illustration. You drop the cone, it will penetrate into the soil, and there will be penetration. So you have to measure that depth of penetration. So basically, the standard depth of penetration for this is 20 mm. So if you have obtained 20 mm on the first trial, as you drop your cone into the soil sample, obtaining the moisture content for this, you have now your liquid limit. However, if you have not obtained the standard depth of penetration, that is 20, for example, depth of penetration, the first trial was 15, so you have to record that one, and then the moisture content present on the soil. You have to record. Then do another trial. Try to get the value of the moisture, try to obtain the moisture content for that soil, and then you drop your cone and you measure the depth of penetration. Then, for example, you obtain 17, you record that one. Depth of penetration is 17, the moisture content for the trial of the soil sample is 42, for example. So you have to record that one. Then, third trial, you haven't obtained again your standard depth of penetration, you only obtain 19. Then on the fourth trial, of course, there is a corresponding moisture content. Then fourth trial, same procedure, obtain the moisture content, then drop the cone, and you obtain 21. So you haven't obtained, based on your fourth trial, you haven't obtained the standard depth of penetration, which has 20, so that you could identify the liquid limit. So what you're going to do, you're going to plot. You have to plot that one. So you're going to plot along the x-axis the depth of penetration that was obtained through your test and through your trial. And of course, along the y-axis, the corresponding moisture content on each trial. For example, you have here 50, this is 18, for example. What is the moisture content on the first trial? You record that one. Second trial, what was the moisture content? Then the depth of penetration, you record. Then third trial, what was the moisture content? Then the depth of penetration, you record that one up to the fourth trial. Once you have recorded this one, you try to connect the dots. You have to connect the points then, so that you can obtain your liquid limit. As mentioned, our standard depth of penetration is 20. So you locate 20 along the x-axis. So this is 20. So if this is 20, you record, you draw a line upward as it touches the flow curve. Once it touches the flow curve, you draw a line towards the vertical axis, and you try to read the moisture content and the corresponding. For example, this is 48, for example. So this is now, the moisture content is 48. So this is now the corresponding liquid limit for that particular sample. So you have obtained now the liquid limit for that sample. Of course, for this flow curve, this is the you have the same formula for the flow curve. However, for the flow index, this is the you have a different equation for the flow index based by the Casagrande method and the Falcone method. So this is the formula for flow index using the Falcone test. So then afterwards, you simply have to substitute this I sub f, or the flow index, to our formula in our flow curve that was presented a while ago. So for example, for this liquid limit, for this Falcone method, on the first trial, you obtained depth of penetration was 20. So of course, 20 was the standard. So automatically you're going to stop with the second, third. No more trial to be conducted. And since you have obtained depth of penetration 20 and you have recorded the moisture content before the trial started, so that moisture content is now your liquid limit. For example, on the first trial, still you did not obtain 20, you go on with the second trial. Once you obtain 20 on the second trial, for example, you stop. There will be no third trial or fourth trial. So the corresponding moisture content for that D, or depth of penetration, which is 20, that is now the liquid limit. So that is for the Falcone method. So that was our discussion for liquid limit. So we move on to plastic limit. So if the water content, for plastic limit, if the water content at which the soil changes from plastic to liquid behavior, the plastic limit is the water content. So the plastic limit is the water content in percent at which a soil can no longer be deformed by rolling into 3.2 mm diameter threads without crumbling. So the plastic limit is defined as the moisture content in percent at which the soil crumbles when rolled into the thread of 3.2 mm in diameter. The plastic limit is the lower limit of the plastic stage of soil. The plastic limit test is simple and is performed by repeated rollings of ellipsoidal-sized soil mass by hand on the ground glass plate. So this is the illustration for our plastic limit. This is given by the ASTM, American Standard Testing Materials. It is it is identified in test designation D-4318. So this is how you're going to perform your plastic limit. You're going to roll a 3.2 mm diameter thread of soil without crumbling. So that is how plastic limit is being defined, is being illustrated. So the full cone method may also be used as in the liquid limit, but using a cone with a mass of 2.35 Newton instead. So basically for our plastic limit, you're going to, you can make use of the full cone method, wherein in the full cone method, you're going to have still the procedure as the same, what we have done on our liquid limit, how you're going to obtain the trials. Still, the depth of penetration is 20, that is the standard, and if you obtain the depth of penetration on a particular trial, which is 20, the corresponding moisture content, that is now the value of the plastic limit. However, if you haven't obtained depth of penetration, which is 20, you're going to have the same procedure as we have in our liquid limit, a series of trials. Then after a series of trials, for example, for 4 trials, you're going to plot the moisture content in the cone of depth of penetration of the cone. Then you're going to connect the dots, and from the x-axis, you're going to obtain the depth of penetration, which is 20. Then you draw a line towards the flow curve. You draw a line towards the horizontal along the moisture content on the y-axis. You get approximately the reading for the moisture content that is now corresponding to the plastic limit for that particular soil. The only difference for the liquid limit and the plastic limit using the full cone method is the weight of the cone that you're going to drop. In the liquid limit, it is more lighter in weight compared to the plastic limit. On the liquid limit using the full cone method, the cone is 0.78 Newton. However, on the plastic limit, the cone is heavier, which has a weight of 2.35 Newton. However, it's the only difference, the weight of the cone that you're going to drop on the soil sample. But the procedure, the standard of the depth of penetration, they're the same. So for that, based on what we have obtained now, we have obtained our plastic limit and the liquid limit. Basically for plastic limit, before this plasticity index, basically plastic limit analysis is concerned with the problem of finding how strong a given structure is. Basically, it estimates the factor by which the live load component needs to be amplified so that the structural crisis, which takes the form of a plastic collapse, occurs. Plastic collapse takes place when the structure is converted into a mechanism by the development of a suitable number of disposition of plastic hinges. So for this one, plastic collapse factor represents one of the most important outcomes of a plastic structural analysis, and it is useful for the reliable and economically safety and assessment and design of a ductile structure. So basically, that's the importance for plastic limit. So once we have obtained the plastic limit and our liquid limit, we can have what we call the difference between the two, between the liquid limit and the plastic limit, and the difference between the two is what we call plasticity index. So when we talk about plasticity index, it is a measure of the plasticity of a soil. The plasticity index is the size of the range of water content where the soil exhibits plastic properties. The plasticity index is the difference between of course, the liquid limit and the plastic limit. So this is basically the formula for obtaining the plasticity index. So we have a correlation of the plasticity index and the flow index. Of course, we have identified what is a plasticity index, and we have also identified what is a flow index. So the correlation